Hi everyone, my name is Drew Paroski, and today I'm going to be talking about a software project called HHVM that was developed at Facebook and why C++ was our language of choice for building HHVM. First, we're going to give a quick overview of what HHVM is, just so you can follow along, and then we'll get into the fun part, which is why C++ was a great choice of language. And before we get started, just a little about me. My name is Drew Paroski. I've been at Facebook for about 5 years. And I've worked on the HHVM project since its inception in 2010. And before that, I was working at Microsoft on improving the performance of the common language runtime. So I did some targeted improvements to the engine and the JIT compiler to try to speed things up. So without further ado, first question, what is HHVM? It's an acronym, stands for Hip Hop Virtual Machine. And it's basically a JIT compiler for the PHP language, and also another language that's a spin-off of PHP called Hack, which was developed in-house at Facebook. And unlike a lot of JIT compilers, the HHVM's JIT is trace-based. And we'll get to what that means in a second, but the gist is it's sub-method granularity. It doesn't do a whole method at a time. And why a JIT instead of other approaches? Well, it preserves the flexibility and the productivity that PHP developers are accustomed to. And it allows us also to support the entire PHP language. It's a very dynamic language, supports things like eval. So it was important to have a JIT so that we could support the entire language. And HHVM is used at Facebook. The reason it was developed is because Facebook had a large investment in PHP kind of from its beginning in 2004. It had a code base written in PHP that grew very quickly during the first couple of years. It grew about 3x in terms of line of code for the first couple of years. And then, this code base became very valuable. But as it became bigger and as Facebook took on more and more users, the performance really started to matter. The stock PHP interpreter wasn't really cutting it. And so HHVM was developed to solve that problem. And HHVM wasn't the first solution that Facebook developed to help improve performance. It evolved from a previous project called HPHPC, or Open Source's Hip Hop for PHP, which was a transpiler that converted PHP into C++ and then compiled that. So as of the middle of this year, HHVM, together with HPHPC before it, has realized over about a 10x increase in throughput over the past 5 years or so, past 4 years. And it's also reduced memory usage a lot, over 75%. And this was comparing it to the version of PHP 5.2 that Facebook was using back in 2009. So just a couple quick caveats. We're comparing HHVM today to a version of PHP from 5 years ago. And this isn't one measurement. This was actually multiple measurements over time, different deltas that were stitched together to come up with these numbers. And the reason we did it that way is that Facebook's code base for a while now has not been able to run on the stock PHP interpreter. It started using features that were only available in HPHPC and HHVM. So a direct comparison, no longer possible. And the whole point is to build less of these things. Facebook, as you know, has a number of data centers across the world, and there's these giant buildings just filled with rows and rows of computers, and they have to be powered on 24/7. You have cooling systems. So it's not just the hardware. It's keeping these things on and up and running is really expensive. So the fewer web servers we need, the fewer engines executing PHP we need on machines, the better. The fewer of these we can build, and the cheaper we can run the site. So I should note, I showed you guys a comparison of HHVM today versus PHP from 5 years ago. There's been a lot of improvement in the stock PHP interpreter, so I didn't want to hand wave over that. They have notably improved. But nevertheless, if you take HHVM and compare WordPress or various applications out of the box, you'll still see about a 2x gain for a lot of applications, sometimes more, compared with the PHP 5.5 with the opcode cache. Earlier I mentioned that part of HHVM's mission was to preserve that flexibility and productivity that PHP developers are accustomed to. And what I meant by that was that PHP developers are used to this edit, save, run workflow, where they can open a PHP file, make a few changes, hit save, hit refresh in their browser, and bam, they see the changes. They don't have to do a manual build step that takes a human perceivable amount of time or they have to wait. And so you get this rapid iterative development workflow where, for those of you who code in C++ or other languages that take a little while to compile, you know that it kind of ruins your workflow when you have to take a break. You have to be very active to switch to something else for a few minutes and then switch back. Anyways, very productive to be able to make a change and then immediately see. And so HHVM supports this. It's able to detect when a file changes on the file system, and it doesn't have to rejit everything. HHVM was designed so that a few files can change, and then it only needs to rejit part of the code, but it can reuse most of what it's already jitted from previous requests. So that was kind of a design consideration with HHVM. Next question you might be wondering is, well, what can this thing run other than Facebook.com? Up until recently, the answer was not that much, but in the past 2 years, there's been a lot of effort to make it compatible, to kind of try out all these different popular PHP frameworks out there, work out all the kinks, figure out all the bugs. And so now we're able to run quite a bit of, a large number of your most popular PHP applications. So you may have heard of MediaWiki. That's the software that runs all the various wiki sites across the internet. So that software can be run on HHVM. You've also got WordPress, a very popular blogging platform, and just dozens of other PHP frameworks now can be run on HHVM. So now you know what HHVM is. Next question is, just a little internals. How does it work? The gist is that PHP gets parsed, it gets converted into bytecode and metadata, and then a basic block at a time. We call them tracelets because they're not exactly basic blocks, but basically a basic block at a time gets translated using the live type information. So the engine waits until that basic block's about to be executed. It's able to observe the current types of the locals and any temporary variables. And then it is able to generate a typed intermediate representation for that basic block. Now that it has live type info, it can kind of do type analysis. And then finally, we take that typed intermediate representation and it gets converted down into x64 machine code. So here's your basic pipeline. This oversimplifies things a bit, but it's the basic gist. You start with PHP source. It briefly turns into an abstract syntax tree, which then changes into bytecode and metadata. And then it can be interpreted, but the main route that we take, so that we get good performance, is to turn it into that typed intermediate representation I was talking about. And then that ultimately turns into x64 machine code. So at the bottom, it kind of has a picture of what's running on the CPU. So it's kind of a mix of three things. You have the generated machine code, then you also have the runtime. So the runtime provides various little helpers that are written in C++ that deal with very common operations, string manipulation, some stuff with arrays, things like that. And then you also have an interpreter which can run from time to time. Obviously, we try to avoid leaning on the interpreter too much, but it is an option. It is something we can switch to when it suits us. We'll walk through a real quick example of how PHP turns into machine code on HHVM. So you don't really need to understand the bytecode here, but it's just kind of shown for demonstrative purposes so you can get a feel of what it looks like. And the function we're showing here, f, essentially has three basic blocks. The first one is shown by that first arrow, is evaluating a condition. And then the second two are the if and else parts of the if-else structure. So the second and third arrow show you kind of how those pieces of source line up with chunks of bytecode. And once we hit a basic block of bytecode that we want to execute, we take that bytecode and then we observe live type information. For example, maybe local ID 0 is an integer and local ID 1 is a string. The dreaded Java install. And those two together are taken to generate a tracelet. And tracelets basically have three parts. You have the beginning, which is the type guards. They make sure that the types are what the body assumes they are. If the types don't match, it jumps somewhere else to handle execution. Then you have the body, which does the actual work. And then finally, you have something at the bottom that kind of figures out where to go next. And putting it all together, we have our example function f. So let's say it gets called the first time, a is an array, and k is an integer. And what you'll see is you generate this first basic block who has the type guards, as I mentioned, and then has the body that deals with evaluating the condition. And there's three possible control flow paths out of here. The first one, you'll see an arrow coming out of the right to stub labeled retranslate. This is where we jump if the guards fail. So initially when a tracelet's generated, it points to a retranslate stub. So if the guards fail, that stub will call back into the JIT and it'll deal with generating another translation for a different set of input types. And then at the bottom you have 2 more control flow paths, which are stubs to generate the code for the next basic block. And because this is an if statement, there's 2 possible paths, one if the condition evaluates to true and one if it evaluates to false. So let's suppose the condition evaluated to false this time around. So then that translate stub will get invoked. The JIT will now generate a translation for the next basic block that we're about to travel to, which is the else clause. And in this case, we don't need a type guard on A because A doesn't get used. We only need to know that K is an integer. And as before, we have a stub that goes to retranslate if that guard fails. And then not shown in this diagram, of course, there's control flow to deal with returning to the caller, but it's not important for this example. So now let's say F gets called a second time, but this time, instead of K being an integer, K is a string. So what will happen is you'll enter those type guards will fail, you'll go to the retranslate stub, and now the retranslate stub will generate a second tracelet for that same source location. So now that the if condition has 2 different translations corresponding to it. The second one can deal with K being a string and A being an array. So it does the same thing, but it's type specialized for different input types. And once again, we have our 3 possible control flow paths. Let's say this time around the condition evaluates to true. So that translate stub will now generate a translation for the if case, where K is a string, and once again, we don't care about A because it's not used in the if clause. So that gives you a pretty quick overview of kind of what it looks like as code is executing, how tracelets get generated, how they get stitched together organically as the program executes. And just putting it all together for those of you who like looking at machine code, you have just a quick sample of 3 times n plus 1, and then we're storing it back into that local n. That turns into a chunk of bytecode that's untyped that does the equivalent of that work. So that mul instruction in the bytecode can handle any input types. It's not integer multiply or floating point multiply. It just multiply and it'll do whatever type juggling is necessary. And then that ends up turning into machine code. After turning into IR, it gets flattened. Those first 2 instructions, the comp and the J&E, are the type guard for this for this tracelet. So this tracelet wants to know the type of n. In this case, n's an integer. So it's checking to make sure n's an integer, and then it reads the local out of the memory location into RAX, and it does the actual times 3 and plus 1. One last thing of interest that we'll be touching on later in the talk, it's just important to understand how the flow of execution is modeled in HHVM, how it keeps track of what the program's doing. And so like a lot of languages, it models it using a call stack. You have a stack of frames. The frame at the top represents the function invocation that you're currently inside. And then all the frames below it represent who to return to when that frame exits. And we have some frames that correspond to C++ code, and then we have some frames that correspond to PHP code, which we call VM frames, and they're shown in purple. And the C++ frames are shown in light blue. And it's just important to know that you have a mix of these 2 in the call stack. So initially you start in HHVM's main function, which is written in C++. It does some various initialization. It goes through this enterTCHelper kind of transition function. We'll talk about that in a little more detail later in the talk. Then that can enter into JITted code, as shown by the purple. And the one other important thing is that, of course, to make various built-ins work that deal with I/O or other stuff that has to be native, PHP can call into the C++ functions. HHVM has the ability to do that. In this case, we're calling the array map built in. And then another key detail is that the C++ you call into can then call back into PHP. So I picked array map because it's a callback-driven API where you pass it a PHP callback that you want to be evaluated for every element of an array. So it's handy to know that you can have this interleaved call stack where you have a mix of C++ frames and VM frames that represent PHP functions. So now that we got all that technical detail out of the way of what is HHVM, why do you care, how does it work, now we get to the fun part, which is why was C++ such a great choice for building HHVM? Why didn't we use any of the other alternatives out there? In one sentence, the answer is C++ hits this great sweet spot for building language VMs. On one hand, you have superb control and performance. So the only other language you probably have more control in is assembly, but you have really close to that level of control, really close to what the machine code ends up being, and you can squeeze out pretty much almost every last ounce of performance you want. But then you also have a lot of features, if you want to use them, you have the option to. That's one of the great things. You have this fine-grained control to use features that make your life easier. You make things more convenient, or to make code more maintainable, or to have more safety so that you're less likely to do something that makes your process crash. And maintainability is key. Otherwise, we would just write the whole thing in assembly, but that's terribly unmaintainable. So C++ hits this nice spot in the middle. And it just, the performance is just better than pretty much any other language other than assembly. And again, assembly is just not maintainable, so it's not really an option. And yes, certain features in C++ are not free, but you can be judicious about which ones you choose to use. How much do you choose to use virtual methods or other features that have some runtime cost. So if you use it judiciously, it's pretty much the best performance around. And you have this incredible control. Some key stuff that was really key for HHVM was being able to manually manage memory, not having a lot of languages, Java, C#, if you stay within the safe part of C#. They don't let you do manual pointer arithmetic or unsafe casting. They kind of try to keep you in a box, and that's good for most applications. Safety is good for most applications, but when you're writing a language VM, you want to be able to do unsafe stuff. So that you can write your own memory allocator, or so you can squeeze out that last little bit of performance in some critical parts of the code base. And I mentioned unsafe casting, that's kind of bread and butter, but also being able to control field size. Not all languages have different types, different size integers. So it's great to be able to only use a byte or only use 32 bits when that'll suffice. There's a lot of cases where we don't need a full 64-bit integer. And controlling the layout, again, important. We're generating machine code that's going to have to interact with the layout, so it's important that we're able to control what the offsets are, or at the very least discover what the offsets are, so that we can generate machine code that might read a struct that was defined in C++. And then finally, that kind of bleeds into the last point, which is you have just this great, incredibly lightweight interop with assembly and with machine code, which again, if you're writing a language VM that's a JIT compiler, you really, really need that. And yeah, just tons of convenient features that you can use as little or as much as you want as it fits your needs. Virtual methods. We didn't actually use multiple inheritance, but you can do that if you want. Unsafe casting versus using runtime type information with dynamic cast, so that you can kind of get safe casting and get exceptions or null pointers if the cast isn't successful. You can go the plain old data route, or you can write classes with constructors and copy constructors and destructors. You can use raw pointers all you want, or you can have a smart pointer mechanism that does ref counting so that you don't have to be as engaged in determining when it's time to free something. And then, yeah, being able to control whether something is allocated on the native stack or whether you're allocating it on the heap. And then, just other really useful features, templates, macros, also Lambdas. I don't have them listed here, but Lambdas are excellent. And so, we could start anywhere, but templates is as good a place to start as any. So templates they're fantastic for maintainability and far more hygienic than preprocessor macros. So we always prefer to use templates instead of doing it the macro way. And templates are useful in different ways for different kinds of applications, but for HHVM, what made templates so useful was that certain critical parts of the engine, we really need to be able to inline as much as possible to improve perf. We want to make sure that we don't branch on things, or we have as little indirection as possible. But at the same time, we don't want to write 5 different versions of a method. We want the maintainability of having one template that you can kind of instantiate in different ways. You can plug in different things. So the 2 key things we exercise templates to use. The first I mentioned is eliminating branches. So a lot of languages, you just don't have a feature that lets you do this. On the left-hand side, we have a regular Boolean parameter b, and then we have a conditional call to bar, only if b is true. And I don't know how many of you guys are fans of machine code, but you can tell that the machine code on the left is longer than the machine code on the right. There's a branch, there's a test, there's a branch instruction wrapping around that call. And that's more expensive. You're using up branch prediction resources and cycles on the CPU and so on. On the right side, we made bool b a template parameter, and this works as long as we know what b is at compile time. And the great thing is now 2 copies of foo will get generated by most C++ compilers. One where we know b is true, and so there's no need to do the check, we just unconditionally call bar. That's the machine code that's shown here. And then there's the other version where B is false, in which case that if B call bar turns into nothing. It completely goes away. And so as you can see, yeah, we were able to get rid of some of the branches. And then I also mentioned reducing indirection. So here's an example where we have a function pointer. And on the left-hand side, we're doing it without templates. We have a function pointer that doesn't take any parameters, returns an int. And when you call it, the compiler really can't do anything except generate an indirect call. It reads the machine address out of RDI and jumps to it and does whatever it is supposed to do. And indirect jumps just aren't as efficient as direct jumps that have the address burned in as shown on the right. The CPU just has a harder time speculating where it's going to go. If maybe RDI, because processors are superscalar, do things out of order, maybe the value of RDI isn't available yet, and so the CPU has to stall a little bit until it can figure out where it is. When you have a burned-in address, you never run into this problem where the CPU stalls because it doesn't know where to jump next, and you don't have to deal with speculating and guessing, and then having to deal with what if your guess is wrong. So the right-hand side, the way we make it work is we have a class T, and then we call some well-known static method on it. And that basically is just able to generate a direct call. And again, only works if you know what T is at compile time. Sometimes you have to use function pointers because you don't know until runtime what you're dealing with. But really, this really came in handy when there was certain core parts of the engine that we just had to make as fast as possible. I'll give a quick shout out to Lambdas. Really awesome that they got added to C++. There was, of course, ways to do what Lambdas do without having a formal feature. But what makes them so great is you just are able to have all the related pieces of logic all in one place instead of having to, if you're in a function, sometimes if it's a big function, you have to scroll up and find empty space at the top level, and then you roll your little class that defines operator parentheses or however you're doing it. And now you don't need to do that. You can just use the bracket syntax to denote the beginning of a lambda and just write your logic right in line. And there's a lot of different ways to use C++ lambdas. The way we use in particular is capture everything by reference. So you'll see the bracket, ampersand, close bracket. So that's typically what we use. And you can get burned when you do this, but we're careful to basically make sure that we only pass lambdas into functions, but we don't hold on to them or return them or do anything else that would make the lambdas outlive the variables they're capturing by reference. And the other sweet thing is, you have your lambda inline, so it pretty much always ends up in the same compilation unit, the same CPP file as the thing that's invoking the lambda. So you don't need a special linker that does cross-module inlining or anything. The C++ compiler will be smart enough to be able to inline the lambda or do all kinds of other tricks, which essentially makes the lambda free. Like I said, you can use lambdas in different ways where they aren't free, but we're able to use them in a way which literally does not cost anything extra than the way we were doing things before C++ 11, or rather before we adopted C++ 11 about a year and a half ago. This is just a quick example of, in case you were wondering, what does it look like? In some of our code gen logic, we have this handy if-then-else function, which you can pass two closures, and it'll deal with generating the branch instruction based on the condition. In this case, we're using the Z flag. But it'll generate the branch, and then it'll generate the two bodies of code using the two lambdas you passed in. So it's just neat to be able to do that right in line and be able to have this nice, if-then-else helper. Rather than, you can imagine how this would look a bit clunkier without lambdas, where we would have to define stuff out of line. Now, I did knock the preprocessor a little bit for being unhygienic, but it is just so powerful that you just can't ignore it. There are certain cases where it's just super, super, super useful. And if you use it right, it can actually help with maintainability. Usually, the preprocessor is derided as hurting maintainability or making things harder than other alternatives. But there's one technique called the X macro technique. If you use it right, just can really improve the maintainability of your code base. So we used it in a couple places, but kind of the most notable place we used it was the definition of the bytecode instruction set. So basically, by using this technique, it made it very easy to add or remove or change how bytecode instructions work. And you still have to update a couple of places in HHVM when you do that, but it would have been way more if we hadn't used this technique. So I'll talk about how it works. Basically, you define, in this example, it's called opcodes, and then it's a list of things that kind of look like function calls. In this case, we used O. So it's just a series of O, open paren, list of stuff, close paren, then another O, and so on. And so we have one row for each instruction. As you can see, the instruction name is first, and then the other 4 fields are information about what the inputs or the outputs are, various flags. And what you can do is when you want to leverage this table in different settings, you define O to do whatever you want to do. Then you use the opcodes macro, and then to be hygienic, you undefine O. And so in this case, this is a simple example. We just wanted an enum that had a name for every instruction and would just assign them default integer values starting with 0. So here we define O, and it only takes name, and then we use ... to basically say whatever. We're not going to pay attention to the second, third, or fourth, or fifth thing in each row. We're just looking at the first thing. So that's a simple use, but there's more complicated uses you can do here. So you notice in the third column and fourth column, there's some things that say 1 or 2. So we can actually have hierarchical structures, lists within lists. And the way you take advantage of this is you define O, and you use the token pasting operator. And in this case, it's only using the third column, which is it calls push. And so it basically uses token pasting, puts push underscore in front of that, and now that'll turn into push underscore NOV, or push under 1, or push under 2. And then we can define what those do too. And those can turn around and use more token pasting. And so they'll turn it into push CV and push VV in this case. And I took this from an example in HHVM that's actually way, way more complicated, but it doesn't fit on a slide. But this gives you the gist of you can define O to turn into other things with token pasting, and then define more and more, and you can pretty much get it to do arbitrarily complex things with your definitions. So we use this in a number of places. Anything that has to deal with the bytecode, for the most part, we're able to use this X macro technique. Another great thing about C++, unions and field size, just having control over the field size. And unions, they're really useful, particularly PHP, it's a dynamically typed language. So naturally, we run into this problem where we need some kind of struct that can be an int or a string or an array or an object. And that's where unions really come in handy. And the other place that they're super useful is when you have a struct but you have mutually exclusive fields. So either one field will be populated or the other, but not both. At any given time, one or both of them is null, or just set to an invalid value. And you wouldn't normally use unions, but if this struct is super common, or you allocate a ton of them, or you just need to squeeze it to be as small as possible, that's where you can leverage unions. You can now have these 2 mutually exclusive fields occupy the same space. And also, I mentioned field size. Having the different size integers is great. So we're going to dig into how unions and controlling field size came in handy for HHVM. So I mentioned dealing with dynamically typed values. PHP is a dynamically typed language. So typed value is kind of the workhorse of just when we need to talk about a value in a very generic way. It has a union that can represent all the different types. So we have C++'s 64-bit integer type. We have double precision floating point, and we have a bunch of different kinds of pointer types. And in this case, we ended up using a type tag, which is right after the union. It's called data type, and we have the data type enum here on the right, so you can see. So the type tag basically tells us which member of the union is valid. And very few languages have a feature like unions that's essentially free. So just having this kind of power was really useful. And unsafe casts and bit stealing are also kind of bread and butter. We loved using the bit stealing technique. So in the previous example, we ended up having a separate tag field. But a lot of the times when you're trying to condense a struct, and okay, you use a union, and so you've saved some space that way, but you still often need a way to tell which member of the union is valid. Sometimes you have some external thing that tells you, but a lot of times you don't. And so it's nice to be able to steal bits. So pointers often, we use this particular implementation of malloc where we know the malloc memory is always 8-byte aligned. So we know those bottom 3 bits of the pointer are always 0. And actually this is the case with pretty much every dynamic allocator that's in common usage. Is you pretty much always get something that's 8-byte or 16-byte aligned on x64 platforms. So we can steal the low bits, and so we'll get into a quick example of where we use that. So you'll remember this drawing from an earlier slide, and we have the different frames. So the VM frames are represented, the header is represented using the struct we call an ActRec. It's short for activation record. And it has all kinds of useful information, like where to return to, both the machine code address or the bytecode address if we're using the interpreter. And we need it so that we can get a backtrace. PHP has a function called debug backtrace, which you can call anywhere, which gives you like the current call stack as an array of arrays. So we need to be able to make that work. And ActRec, we could make it smaller. We're still working on it. It's a work in progress. But right now it's about 48 bytes. I think it's exactly 48 bytes. And here's the layout, kind of in a drawing with the struct definition next to it. And you can see that we make use of a couple unions. So I'm going to dig into two of these and how they ended up working. So the first one I want to dig into is this, there's a this pointer or a late bound class. And it's that union of mthis and mclass. So without getting into detail, PHP has this feature called late static binding. And the gist is that even for static methods, you're kind of carrying around the equivalent of a this pointer, but it represents a class. So if you have a static method in a base class, and then you have a derived class that doesn't override the method, there's still a way to tell whether you called b : foo or c : foo. There's this little thing called the late bound class that gets squirreled away. That remembers whether you were called through B or through C. And then you're able to use it kind of similar to the way you use the this pointer to call static methods. So it's a weird feature, but it's actually really useful once you kind of see what it can do. Anyways, we had the need to store a late bound class, and it turns out we never need both of these. If we have a this pointer, the late bound class is always equal to whatever the class of this is. So we didn't need both. And then for when you call a static method, there is no this pointer. So we need something that keeps track of the late bound class. So we make a union. And what we did is we stole the low bit. We knew the object data and class, they're both pointers to heap allocated stuff. And so we steal the low bit, and then we make these helper functions that let us distinguish and then safely get or set the this field or the late bound class field. So has this and has class, you'll see we're doing a C-style cast. I could have done reinterpret cast, but I was trying to keep the slide small. And it basically checks, is that low bit set? And it returns a bool. Then once you've checked has this or has class, you can call get this or get class, whichever is the appropriate one to call. The real code in HHVM has asserts to make sure that if you call get this, but has this returned false, that you'll get an assert in the debug build. Again, I omitted that for brevity. And then finally, we have setters, which will deal with setting the low bit for you so that that logic doesn't have to get sprinkled everywhere. And so this is nice, even though ActRec we kind of mostly use in a struct-like way, it's nice to be able to have a little OOP and add some methods. So that if you have an ActRec pointer, you can just say arrow has class instead of having to have a global function named ActRec _ has class. So while I don't touch on it specifically, OOP has come in handy a fair amount with HHVM. We use it when appropriate, but we're not religious about it. But it's a leg up that C++ has over C, is having the option to do that. One more quick example. This one isn't a union, it's just a 32-bit int, but you'll notice it's called numargs and flags. While we had this 32-bit numargs, we didn't really need all 32 bits. The odds that you're going to pass 2 to the 31 parameters, you're going to run out of memory or some other thing is going to blow first. So, we needed an extra bit somewhere. We couldn't resist the temptation. So we stole the high bit on this one. And again, same pattern of, you have numargs, which masks out the high bit for you. You have the thing that checks the high bit. In this example, we were using the high bit to keep track of whether this activation represented a constructor that was invoked via the new operator. I won't get into it, but those kind of constructors invoked by new need special treatment for exception handling, so that's why we needed the bit. And so yeah, same deal. And then you have your two setters, one that stores numargs and asserts to make sure you don't have the high bit set, and then the other one which will set the high bit for you. And that second setter is the one we use when we're creating a constructor frame that was invoked via the new operator. Shifting gears a bit, another sweet thing about C++ is that it has an incredibly mature ecosystem that has awesome tools for all kinds of things. But the tools I want to focus on for the next couple minutes are profiling tools. So different platforms have different ones. We use Linux predominantly for Facebook's web servers. And so we use the tools that work on Linux. So Linux kernel, a couple years ago, now it comes standard, there's this tool called perf. And you can use it basically uses a sampling technique, and you can use it to figure out where is your program spending all of its time in terms of which functions does it sit inside. And every sample gets the full call stack. So not only do you know which functions are you spending the most time in, but you can see how you got there. You can drill in and see, okay, I'm in function compute foo. Well, why am I calling compute foo? And you can say, okay, 50% of the time I was called this way, and 25% of the time I got called to this other function. So yeah, Linux's perf tool is really great. You can use it to profile one process, or you can use it to profile all the processes on a machine all at the same time. And not all profilers work like this, but Linux's perf tool works by walking the RBP chain to get the call stack. So on x64, what the RBP chain is basically you can start with the register RBP along with RIP. They kind of form a tuple. And from there, you can kind of chase RBP, and you have these little 16-byte frames in memory. So RBP points to the previous frame, and then that's another pair that's prev frame pointer and return address. And so you can get this series of return addresses, starting with RIP, then that first slot up there, then the next one. And then, of course, by taking machine code addresses, you can figure out which functions you're inside, because every function has a range of machine code, so you can consult the table. And that's how Linux's perf tool is able to figure out your call stack. So to make this work in C++, you have to make sure you don't omit frame pointers. So you can force that using the no omit frame pointer flag. If you don't have it, then Linux perf tool won't be able to walk your stack. So what does this have to do with HHVM? Well, we wanted to be able to use perf. We didn't want to have to write our own profiler or come up with, or we could try to come up with hacky schemes to fit in, but we actually found a really natural way to do it, which was we made sure ActRec was laid out the same way as native frames, as C++ frames, for that first 16 bytes. So the first 8 bytes is the pointer to the previous frame in the call stack, whether it be another VM frame or it could be a native frame, because remember the stack can be interleaved with C++ frames and native frames. And then we have the machine address that we're returning to. So it has the same format, and then HHVM essentially just makes sure when it invokes PHP functions and creates a VM frame that it stitches it together. It makes sure that the RBP chain is intact, both when C++ calls into PHP and then when PHP calls back into C++, to call native functionality, IO, what have you. And by doing this, Linux's perf tool just worked. There's one other little trick, which is we had to register symbol names and machine code ranges with perf. So I think we just had to create a file in the temp folder that was like process name -pid.temp or something. But when we do that, we're just able to get the symbols, without having to do anything else. So this is just a quick example of what Linux's perf tool looks like when you're running a WordPress on HHVM. And this isn't the whole thing. I just took I scrolled down a page or two and kind of took one of the ones that'd be interesting. So if you see some of these functions start with HPHP : those are C++ functions. That's part of the HHVM runtime. You'll then notice some other symbols that start with PHP : and then they have a path that ends in .php, and then another : and a method name. That's how we represent PHP symbols. So you can see certain functions in WordPress are calling into runtime helpers or various built-in functions. So it's just really nice that we can just use the standard tool that works so great for regular C++ applications on Linux, and we can leverage it to profile. For this example, we ran WordPress on HHVM, and we're like, okay, we've never really optimized it until very recently. What's the low-hanging fruit? What can we go after? It's just really nice to have this unified view. And yeah, you can make it work on other languages with the profiling story, but just I think it really fit in nicely. I think C++ just has a great profiling story, and particularly when you're doing language VMs. And exception handling is pretty much the same thing. We were able to integrate At first we had a hacky solution, but then we were able to integrate and be a little smoother. And because you have that interleave stack, it matters. You'll have an exception that might start in C++, and then maybe it propagates down the call stack and it hits a PHP frame, and you have to make sure that that works correctly. And then same deal, PHP also has a concept of exceptions that can be thrown, and maybe it propagates past all the PHP frames, and it hits a C++ frame, and we need to make that work. So initially we had these barriers that we set up, these little try catches, that basically if an exception was propagating down through C++ frames, we would catch it right before it was about to hit a PHP frame with this try catch. And then we would use set jump and long jump, where basically we would invoke HHVM's unwinder to peel off the PHP frames, and then if it peeled all of them off and it got to a C++ frame, it would use long jump to kind of take the trampoline off the native stack. So it was a little hacky, but like we were able to get it working pretty quickly. I think when we were working on HHVM, we had an engineer who had just joined the team, and he was able to get the basic exception handling like working in like a month or something like that. Yes, there were bugs and whatever, but it was still great that we could have some basic examples work right away. As I mentioned, that set jump, long jump scheme was a little hacky. We eventually refined it. We discovered that G++ offers this register frame built-in, or this intrinsic, which lets you give information to C++'s exception handling system. So you take for granted when you compile C++ that the compiler's squirreling away all of these little tables and metadata that are used in the event of an exception to figure out what needs to be destroyed based on where your instruction pointer is and stuff like that. What we did is we made a general handler. We took the unwinder we already had from that set jump long jump scheme, and we basically called register frame, and we handed it this TC unwind personality callback that we defined, and basically we register it for all the ranges of JITted code. So any generated code, the C++ unwinder knows if I see any of the instruction pointer anywhere in this range, call this function, and then that allows us to handle dealing with PHP frames unwinding. And then when you hit C++ frames, the unwinder sees that it's in C++, and it has metadata for it, and so life goes on. So it's actually a really smooth integration. And again, it's hard to imagine being able to do an integration this smooth in pretty much any other language that supports exceptions. So now I'm getting to some of the gritty stuff with machine code. As I mentioned at the beginning, it was key that we had lightweight and very efficient and easy machine code interop, because this is a JIT compiler, and we're going to have C++ calling into JITted code and JITted code calling into C++. And a big thing was having a well-defined ABI for function calls. C++ actually defines, here's the registers that are used for passing parameters, and here's the mechanism by which calls are performed and how returns are done. It nails that down. So it's not like you're just reverse engineering, oh, this is what my compiler happens to do. It's actually specified. And I said, okay, C++, it's easy to call into machine code. There's some caveats. If you're using types that have copy constructors and you're passing them by value, or you're returning one of those kind of types, or if you're calling a virtual method or whatever, it's a little trickier. But if you just stick to non-virtual functions or non-virtual methods, and you're using pointers and primitive types like int and double, it's really, really easy. And so that, I guess the ABI that I was just talking about has to do with, I want to generate machine code that calls into C++. Going the other direction is also pretty easy. So let's say you run your JIT, it mallocs some memory, it calls whatever it needs to call on the OS to make sure that range of memory is executable, fills it in with some machine code. Okay, great, now what? So let's say you now have the address of the beginning of that chunk of memory that you just spit a bunch of machine code into. Let's say you have it as a void pointer, get machine code address returns it to you. And now you want to invoke the thing. Well, you can just use unsafe casting. So you have a function pointer type. In this case, let's assume that we generated machine code that's expecting an int and is planning on returning an int following the C++ ABI. And so we can cast that void pointer to a function pointer, and then we can just invoke it, passing it 1, 2, 3, and we get the result back and store it into a local variable. Earlier, you may have seen there was a little, when I showed the interleaved call stack of C++ and PHP frames, there's a little trampoline that dealt with how to C++ go into PHP that was called enterTCHelper. So it was just neat that we were able to do kind of this integration of, we wrote part of it in assembly, then we gave a definition for the assembly part with this extern declaration at the top, and then we rolled the C++ function which calls into the assembly. And we have a little asm volatile thing here to let it know this assembly does not respect preserving registers for the calling convention. So again, something you probably would not be able to do in any language other than C and C++. You're able to tell the compiler, like, I'm doing something shifty here, so you have to be careful with registers. And basically what this trampoline does is generated code in HHVM doesn't use the same calling convention or the same register scheme or what have you that C++ does. And it has certain permanent registers it expects to have certain values. So in particular, R12, it uses as its thread local storage. It comes up a lot, so we just wanted to have it in a register so that we could just access an offset off of R12 really quickly anytime we needed to do thread local stuff. And so what this trampoline does is it sets up the permanent registers, RBX, R12, and RBP, to what the JITted code is expecting them to be. That call instruction enters JITted code. And then whenever JITted code hits a situation where it needs more JITting to happen, it can just return, and it falls back into this trampoline. That pop RBX is actually saving or restoring what push RCX stored, which is that trec info pointer. And then it's able to fill, when JITted code returns back to this trampoline, it just copies RDI, RSI, a bunch of the other registers into this trec info field. So it actually makes it really lightweight when the JIT wants to have a service request, say, I need more stuff JITted. It just moves a couple of values into a couple of registers and just returns. Then this trampoline takes care of moving those registers into some memory. Then you fall back to C++, and this enterTC function actually gets called in a loop that deals with service requests. And of course, there's ways to break out of the loop when appropriate. But there's this, the real things are more complicated. HHVM is open source, so you can go look at the code if you search for enterTC. But we do some neat stuff with the trampoline, the transitions between C++ and JITted code. So that's it for the most part for machine code. I'll have a couple other little examples, but that was the machine code interop part. So I mentioned manual memory management being a big deal. C++ gives you the freedom to manage memory however you want for the most part. And this was important because to get PHP semantics right, it was actually less risky to go with a refcounting approach. Certain language features in PHP actually depend on refcounting if you want to exactly match what the PHP interpreter does. One of them is it has precise destruction. So there's these destruct methods, and the PHP interpreter invokes them the second an object's ref count drops to 0. So they're not like finalizers where they run sometime later. They run immediately. And most programs don't depend on this, but there are some real PHP programs that depend on it. And there's also stuff with arrays and copy on write schemes that involve ref counting. So for a bunch of reasons, just GC wasn't an attractive option at the outset. Also, HPHPC already did ref counting, and so it was kind of easy to just stick with that option. But being able to control how memory allocation works natively. The other cool thing, we get to pick which allocator we use. So there's a lot of different allocator implementations out there. Unfortunately, the one that comes with G++ by default, or at least the version we're using, is a little subpar for if you're doing multi-threading and a lot of allocating in different threads. So we chose to use an allocator. We were initially using TCmalloc, and then we switched back in 2010 to using jemalloc for handling calls to malloc and free and calloc and so on. And jemalloc is actually developed by Jason Evans, who's one of the engineers who started HHVM back in 2010 together with me and Keith Adams. So it was great having him on the team. Obviously, he knew the allocator very well. And like I said, really efficient. It's the default allocator in FreeBSD, or at least it's the one the operating system uses. It's also used in a couple of versions of Firefox and a bunch of other software projects. And what it really excels at is minimizing fragmentation for long-running processes. And HHVM being a long-running server-side process, that runs for 24 hours or more, depending on how you use it, it was important that we kept fragmentation to a minimum. But one of the really cool things that it came from the fact that we were able to pick our own allocator was that we were able to get this coevolution between HHVM and the jemalloc allocator. So HHVM takes advantage of some jemalloc APIs that aren't part of the standard malloc interface. So in addition to the standard ones, jemalloc offers a couple extra APIs with more options. And one of the options it offers, one of the options that got added just for HHVM was the ability to allocate memory that has low addresses that can fit inside 32 bits. And we'll get into, in a second, we'll get into why that's helpful. And then another thing is that a lot of sophisticated heap profiling functionality got added to jemalloc over time. And the main motivation for doing that was to be able to profile how HHVM used memory and improve it over time. So low memory addresses, the gist is they basically let us make structs smaller. If we can guarantee that certain structs are always allocated in low memory, well, now we can store them using int32 instead of int64. And unsafe casting, like I said, is our bread and butter here. So we define a little getter and setter, and now you can get and set class pointers to this low class putter field. Again, the real code has asserts and stuff to make sure that the address you're handing it actually does fit in 32 bits. I omitted that for brevity. And so not only do you make structs smaller, but you end up making machine code smaller. So the JIT a lot of times will need to burn in a class pointer into machine code as an immediate. And if that immediate is 32 bits, you see it fits in this example, we're trying to move the immediate into some memory location. The top shows what it looks like when it's 32 bits. It's one instruction, and it takes up 7 bytes total. And compared to if it was didn't fit in 32 bits, you end up having to use 2 instructions because x64, the machine code, the only instruction that can deal with 64-bit immediates moves it to a register. So you have to move your immediate to a register, then you have to move the register to memory. And the result is actually twice as large. The machine code is twice as big. So by doing this, we were able to reduce machine code size for these cases by 50%, which is pretty nice. And normally you don't think about machine code size, you just kind of take for granted the compiler does a good job, but when you're generating the code yourself, you have to pay attention. And just like making structs smaller, machine code size matters for performance. The smaller you can make machine code size, the less iCache misses you take, particularly when you have a big program. We end up generating, over 100 megs or something on that ballpark of JITted code for Facebook's application. So we were taking a lot of iCache misses, and doing this kind of improvement, noticeably moved the needle for making the site more efficient. Another thing, PHP is an interesting model for concurrency. It organizes things in requests. Every request is single-threaded. They all have their own distinct heap. They can't directly access each other's heaps. And so it was nice to be able to control allocation because we rolled our own request allocator. And it basically took advantage of a lot of optimization opportunities. There's a big opportunity at the end of a request of just the whole heap is dead. So aside from having to run destruct methods or something, most of the heap you can just throw away all at once instead of having to iterate over each thing and free them individually. Also, by controlling the allocator that's used by the PHP new operator and so on, it lets us make JITted code integrate with it better because we control what the allocator does. We can inline the fast path of the allocator into JITted code, and then we only need to call out to deal with the slow path. Finally, huge pages. Another thing where being able to control the nitty-gritty is helpful. And this is similar to the iCache miss issue. Basically, there's this thing called the ITLB. You take it for granted. It's this little piece of hardware. It converts virtual to physical addresses for you. But because it's hardware, it's got this hash table that's a fixed size. And when it gets too clogged, things get evicted. And so if you have a lot of machine code, you end up using up a lot of ITLB entries. And if you have enough, they keep evicting each other. So you keep taking ITLB misses, which are pretty expensive. So Linux now offers this API through madvise, or this feature through the madvise API that lets you tell it, the hardware, hey, for this range of addresses, try to use the larger page size, which means that you use fewer ITLB entries because you now only need 4 instead of 40 entries to represent so many megs of memory. And that results in fewer ITLB misses and, again, better performance. So there's a couple obstacles with C++ in particular when we were building HHVM. But what I want to really drive home here is that it's really a testament to C++'s power and flexibility that we were always able to find a way to hack around the obstacles, or almost always. So we ran into this situation where we had two non-POD types. They were classes with constructors and destructors and all this, and we needed to make them into a union. I won't get into the details, but suffice it to say, we wanted to make a union of two things, and this is before we adopted C++11. So here's what we did. We made a char array. We made sure it was big enough to fit either object. We used the attribute align 16 because char arrays by default don't get magically aligned for you because the compiler's like, oh, it's a char, doesn't need to be 4-byte or 8-byte aligned or whatever. So we use that attribute align to force it. And then we have these two little getters which do unsafe casting on the char array to pretend it's either an array iter or an M array iter. And then we have two different inits and two different frees. The inits use the placement new syntax, which if you've ever written your own like allocator thing with the STL, you learn about the joys of the placement new syntax. And then we're able to call the destructors manually as well by doing dot tilde class name. Once we had C++11, we were able to do away with this hackery. So you'll notice that attribute aligned thing went away, the char array goes away. We now just have a union. Everything else is pretty much the same. We still do placement new, and we still call the destructors manually. Another thing, before C++11 with the move constructors and R-value references, we'd run into these situations with smart pointers, which would just do unnecessary ref counting. In this example, both variant and string are two different kinds of smart pointers. Variant can deal with all the different types. String, you're pointing at a string data. So let's say you had foo, it happens to return a string, but then you want to store it in a variant. That's going to do an unnecessary increment and then decrement on the ref count. And again, it matters to us. We were trying to squeeze out every last little bit of performance. So it matters to avoid unnecessary ref counting. This was how we hacked around it before C++11. We'd have a special constructor with a dummy arg that knows not to do the increment. We'd have a detach method on string that we would have to call manually at every use site to basically say, let go of this thing and don't decref it. I know what I'm doing. And then here's what the use site looks like at the bottom. We'd have to use the special constructor variant with the dummy param and then call detach on the string. So we kind of had to do two things, to suppress the inc and to suppress the dec. Move constructors, no need to do that. The main win is that you don't have all that crap at the use site anymore. All you have to do is define your move constructor for variant. You still need the detach logic, but now detach is getting called by the move constructor. The calls to detach aren't sprinkled all over the place. And yeah, instance methods gave us a bit of a headache. Instance method pointers can't be cast to void pointers. C++ doesn't let you do that. The reason is that they don't always fit in 8 bytes. So it has its reasons for not letting you do it. But we had all these instance methods in HPHPC. And like I said, OOP is a win. It's nice to use in certain places. So we didn't want to have to avoid using instance methods everywhere. And of course, we found a way to make it work. Unions is the answer. You basically make a union, you cast it to the union star using an unsafe cast, which it lets you do because methputter is one of the elements of the union. So the compiler lets it slide. And then you do arrow putter to get the void star. And now you can see how that we can get the machine code address. Really all we need is we just need to know what immediate we're going to burn into machine code for the call instruction, which is shown at the bottom. And for those of you who aren't big on machine code, this is kind of what the equivalent would look like if you used this technique, but then you invoked it from C++. You're kind of turning it into a regular function pointer. And again, this is ABI specific, but C++ actually defines the ABI, so you can rely on it. Virtual methods, same deal, slightly trickier. Virtual methods, you don't have a immediate, you can just burn in. You have to do a thing where you pull up the vtable, you know what slot to look in, you read the machine code address out of that slot, then you dispatch to that. We eventually did away with most of the virtual methods in HHVM where they interact with, we want places where we had machine code calling into virtual methods. We eventually massaged things so they weren't virtual anymore. But here's how we worked around it. And this only works on G++, x64, and might be broken in future versions, no promises. But basically, we figured out how to, we know that the vtable for single inheritance is always at offset 0, and then the table seemed to store the offsets, but the low bit was tagged. That's what the subtract 1 is doing, is it's getting rid of that tag on the low bit. And then we're able to generate code as is shown here, where virtual call sites end up being 2 instructions. The dereference of the object to get at the vtable footer, and then another call plus dereference together is one instruction to read the desired slot from the vtable and then jump to the address that's held in the slot. And again, for folks that aren't machine code savvy, this is kind of what it would look like if you were to use that technique to call the virtual method in C++. Again, this is not recommended practice. Do not do this unless you have to generate machine code that calls virtual methods. So you shouldn't be writing anything like what's below. Yeah, that's pretty much it. Thank you very much. So I'm willing to take questions if anyone has them, unless we're losing the room. Yes?
So what is the biggest challenge in profiling?
Profiling? Okay, so yeah, the question was, what's the biggest challenge in profiling? And I'm assuming you're talking specifically for HHVM. So you end up having, some generic functions that kind of are, it's hard to tell exactly what they're doing, so a lot of times you have to look at what they're calling. Sometimes we needed to add extra tracing or logging to figure out why we got somewhere. Also, your standard profilers don't answer everything. They answer, like the Linux perf tool gave us good stuff for exclusive time, but we ended up having to write other tools that would parse the data it captured when we wanted inclusive time instead of exclusive time, or like certain other views that are useful. So I think they're, as far as Linux perf tool specifically goes, the viewer that they have when you do perf report could use a little work with supporting more modes of exploration and so on. And then also, it didn't really help with memory profiling, the perf tool. So jemalloc ended up having a bunch of stuff added to it. But memory profiling is pretty much just as important. Once you get all the low-hanging fruit with like clowny stuff you're doing, with spending too much CPU time doing something dumb, memory is a little tricky. So I mentioned like huge pages and some of those other things. Those wins, it was weird. When you take cache misses, it has these like non-local effects. So that won't show up in your standard profiler. And it was weird. We had like an 80-20 split between the JIT and the runtime. We ended up spending like a little under 80% of the time in the runtime and 20% or a little over 20% in the JIT. Then we did this thing with huge pages, which only benefited JITted code in theory. That was the code that was now getting those fewer ITLB entries that were larger, granularity. But the balance between JITted code and runtime code stayed the same because it had this by taking fewer ITLB misses, it had this non-local effect of kind of this a tide that lifts all boats. And just cache misses in general. They're hard to trace down what is causing the eviction to happen. So one of the people I worked on HHVM with, Keith Adams, used this pin simulator thing, which basically simulated a cache in software, and it would run, HHVM at like 1,000th of the normal speed, or like super slow. It took forever to get going, but he was able to simulate the cache, and he had all this logging going on, and so he was able to figure out, usually you see which function suffers from the cache miss, but you want to know like who was the greedy jerk who like polluted the cache and caused that guy to get evicted. And so there were some interesting results, but it took a lot of work to get them. One of the interesting results was the implementation of memcopy that we were using from G++ was so big that it was causing itself to get evicted. Like it's just, it had all these special cases for different alignments of the input and output and whatever. And between all the jumping around it did, it was so big that it was causing other parts of memcopy on a different page to get paged out or to not be in the cache anymore. And so we rolled our own simpler version of memcopy where we know that the addresses are aligned and whatever. I would say, yeah, probably the trickiest stuff about profiling performance is memory and getting a handle on that. Most people who know about profiling know about, CPU time stuff. Any other questions? Yes?
So your work is PHP, but do you think that other scripting languages, Pythons or whatever, would see similar sort of improvements and so forth if you were required? I mean, all the techniques here apply probably, right?
Yeah, I mean, C++, we used it to build a language VM for PHP. Sorry, I should repeat the question. So the question is, sorry.
This is probably would apply to
Okay, yeah. So does the techniques used for HHVM, would they apply to other languages to improve their performance as well? Did I get that capture it? Yeah, so I guess, yeah, the answer is yes. And I think C++ would be very useful for building language VMs for other languages. So I'm familiar with Microsoft's CLR, which was written in C++ and had really good experience. Just the maintainability, the code quality was all really good. Yeah, and various JVMs that I've come across were also written in C++. And yeah, a lot of the techniques used in HHVM I think would work well. Like I said, there's a couple things that are unique about PHP. The fact that it's got this request model of concurrency, that each request is single threaded, that each request has its own separate heap, and the heaps, can't directly reference each other. So like ref counting, for example, we didn't have to use interlocked increment and decrement because we knew only one thread and was going to be messing with the ref count. So there's some stuff like that we were able to do like for that probably wouldn't apply to other languages where maybe they have different concurrency models. But I think the Tracelet style solution, basic block at a time, worked really well at discovering latent types. And that's like the big problem dynamic languages have that your statically typed languages don't have, is that the programmer's not telling you what the types are. You have to discover what they are yourself through profiling or other techniques. And so that's like the main missing piece of the puzzle you need when you want to build an efficient VM for a dynamic language, when you compare it to, say, the JVM or the CLR. Yes?
What's your support for interactive debugging? We talk a lot about profiling and all that stuff. What about the other end of debugging and doing actual application development?
Okay, the question was about what's our story for supporting interactive debugging? Because we touched on profiling a bit. And are you asking about debugging a PHP program or debugging HHVM itself?
Debugging the actual application code, so Facebook PHP.
Okay. So there's actually, I guess that's a two-part answer. The first answer is that HHVM has its own custom debugger called HPHPD that's been out since about 2011. HPHPD was originally part of the predecessor system, HPHPC, and then as HHVM was coming online, it was ported to work on HHVM. And that's where the interpreter comes in handy a lot. Basically, we're able to, when we want to set a breakpoint, we basically make sure that any translations for that basic block are nuked and like become unreachable. So we smash various stuff to basically say, no, do not enter that JITted code, like interpret this basic block. And then in the interpreter, since we're usually JITting, we can afford to make the interpreter a little slower. And then we're able to make the interpreter park at the desired instruction. And then now when you single step through code, you're doing it interpreted. So it actually saved us a bunch of engineering effort where we didn't have to worry about how do you step through JITted code.
Is there ever a disconnect between the JITted and the interpreted that developers run into?
When there are bugs in HHVM, yes, but ideally, other than the speed, you can't tell the difference between executing on one versus the other.
I guess the question is, did you guys run into a lot of bugs?
Yes, I mean, I wouldn't say a lot, but a couple a year where you're like, hey, this test runs differently on the interpreter versus the JIT compiler. And then the second part of the answer for your question is that we recently implemented support for Xdebug, which was a framework that was common with the stock PHP interpreter. And so there's a bunch of tools like PHP Storm and a couple other popular tools. And I don't know if Xdebug, I don't think it's PHP specific. I think in theory this framework could be used for any language. But anyways, the point is there was this existing thing with the community and tools people really loved. And yeah, we wanted to make sure that you could use PHP Storm with HHVM. So the open source, we have about 4 or 5 engineers now on the HHVM team who strictly work on open source. And so they recently delivered Xdebug compat. So I'm not sure if that's quite up and running, but it should be in a couple months if it doesn't work today.
Can you step over native and managed frames?
The question is, can you step over native and managed frames? Are you talking about debugging?
If you're debugging, can I step from PHP into a C frame and then into a PHP frame and follow?
I see.
I've got an exception unwinding or like?
So the support's not that sophisticated if you're using HPHPD or if you're using PHP Storm, either if it works today or when it works a couple months from now. However, you can use GDB. And if you know what you're doing, yes, you can do what you're talking about.
The question is whether GDB could read over your frames.
Yeah, so GDB, we register symbols with GDB. By default, I think the option's off, but you can turn it on for debugging purposes, and then now when you do BT and hit enter in GDB, just like that profiling example I gave, it'll label PHP frames. But then when it's time to do anything interesting, when you switch to that frame, you need a bunch of GDB macros. And so we have a bunch. I don't think we've made them public. I think currently they're on somebody's dev server at Facebook, just like a file on their home directory. But yeah, we definitely need to make those public. So I guess it's similar to SOS for the CLR. CLR, when you were debugging managed code with a native debugger, they had this extension that basically told the native debugger how to deal with managed frames. So it's not nearly as sophisticated as SOS, but same idea. But yeah, we're not anywhere near, say, Visual C++ or Visual C Sharp's debugger. Actually, was Visual C Sharp debugger able to enter into C++ frames, or the runtime itself?
The runtime itself, yeah.
Oh, okay, yeah. So yeah, we're not that sophisticated, but yeah, you can use GDB and pretty much, like I said, if you know what you're doing, you can do pretty much anything you want. Roll your own little GDB macros and so on. Cool. Any other questions? All right, great. Thanks, everyone.